Okay, so thank you very much for having me here. Today I'm presenting a work which is not really, the last thing I'm working on, but this is something I'm interested in, and it's about forecasting asylum-related migration flows using machine learning and data, different resolution and different scales. This is a joint work with Marcello Caramia, which is also in the room, and Teddy Wilkin from formerly EASO agency, now EUA agency. Although I think the most important part of this work is not about really forecasting, it's about how this process that I'm going to present, this model, may provide useful information about these flows. Okay, this was the system that we set up at EASO. So I keep saying EASO because this is when we did this. And it's about taking data from different inputs. This was kind of 5 years ago, 6 years ago when we started. Now all these data are kind of very frequently used data for this type of studies. But anyway, we took data who try to represent instability of the country. So even data from the GDELT repository, which is about daily events by country of origin of different things, including conflicts, social unrest, economic status, and things like that. Then we experimented with Google Trends data, trying to understand whether there is some kind of signal in this data. We took also official statistics like the Frontex data. So these are monthly detection of illegal border crossing on different routes and these are data by citizenship. And then the EASO operational data. So these were not the official statistics, but the operational data, which we're using internally, like to pre-allocate resources for the agency. And then all of this went to a normalization process, what I call the clock alignment and filtering. And once the data are normalized, the analysis starts. So I want to go through all these steps just to share with you this experience. Then the system was composed of two parts, the early warning and the forecasting. But as I said, the forecasting part, although it was quite accurate, and it is still quite accurate in the type of the results that it gives, is not the main focus of my presentation today. So the early warning system was just to analyze these hundreds of time series, because we're talking about like 400 time series entering the system. And we need a way to summarize whether there is some important signal in this data or not to be used later for the forecasting model. So we kind of statistically select the variables rather than just let the machine learning model to do this. So some change point analysis, some lead lag analysis, some momentum approach to see whether you will see that the time series get an unpredicted acceleration or deceleration for some reason. And then it went to the model. What we call the dynamic elastic net is the model that we use, which is an elastic net based on time series data. And then the forecasting part. So I'm going to describe all this system. So first of all, the GDELT. So GDELT comes as a series of events correlated to different type of, there is a code book which describes each type of events and which topic it refers to. We selected 5 categories, or 5 for this study. So conflict, economic events, social unrest events, governance-related events, and political events. And then we need to assign a sign, like this is a push factor or not, this type of event for our type of analysis, and also the strength, because the literature says that, and Marcello is the expert here, that for some reason, this kind of event as a strength for this conflict as an indicator that we're going to be, which is 3 times the decrease of ceasefire for some reason. So I didn't discuss this, I just take it for granted. and so this is how we built the indicator. After that, we built 5 indicators, the J that you see in front of each variable. And this is just the cumulative sum of the events multiplied by the sign on the strand. So the idea is that there might be countries which are in constant, say, small conflicts going around, but at some point this explodes. So the fact that we took cumulative data is kind of to try to see when this accumulation of tension actually generates something like a migration flow. And that's why we consider this. So IASO then built on top of some combination of this, a composite indicator, which is called the push factor indicator, which I think is still in use in the agency to try to monitor the situation in different countries. Then we went to, you know how to eliminate this bar, which I hate? I hate this bar. I don't know. The green?
Oh, there it is.
Thank you. I mean, not entire, but
oh. A little bit. And just click here.
I mean, after 3 years of pandemic, I still not fight with this. Anyway, Google search data, which is something that you can download from the Google Translator. There are no API, but you can kind of construct API for this. It's about searches in the country of origin. And rather than searching for keywords, for explicit keywords, we went for, although the system is configurable, you can put anything in the system, but we decide, so this is a design choice, to go by topics. The reason why we went by topic is that these keywords are aggregated by language by Google through some obscure mechanism, but the idea is that they are comparable in terms of what they mean in the different countries. So in this sense, they are comparable. You have larger volumes because most of the times, if you focus on keywords, you have time series which are 0 or very low value, which are actually not helping the analysis. And of course, depending on the resolution on which you take the data, you can have daily data, weekly data, monthly data, depending on how long you take time series. Anyway, of course, the cons with all this type of data, you know, and there will be several talk on this, is that these are semi-black box, the way they are constructed. So we never know about, I mean, we know about the trends, and this is why it's called Google Trend, but we don't know about the absolute value of this number of search, and we don't know even the denominator of this search. So what is this ratio that we see? Anyway, so it's important to see the trends. And in our objects was just to capturing the trends. Then we took official statistics and unofficial statistics, so not still official statistics like the front-end IBC data by route and the ASO applicants by the dyads, origin destinations. Then we put some other things like recognition rate, calendar holidays, because applications are not really data like arrivals, like IBC or in general arrivals. The reason why is that they are process data. So application, for example, have a cap because this is the maximum number of application an agency can treat by this month or by this week, but it's not related to the number of people really coming. So it's kind of different when you try to model this. So you need to take also into account calendar holidays. So there is a big drop down in mid-August and also at the end of the year. Not because migrants do not arrive in August, especially in Italy, for example. Actually, it's the highest month of arrivals, just because they are on holidays. So the agency do not work those days. I mean, do not work to register the data. So you get the data the next month. And the recognition rate is a way to take into account also the fact that the migration flows also depends on how easy for the migrants is to take some route rather than another route. So we try to capture also this phenomenon. And then the normalization or pre-processing part. So first time we did some kind of interpolation to adjust for time, but also we need to adjust for the definition of what is origin and destination, because data are of different type, as you have seen. So we had to match roots, of course, for IBC, citizenship, for recognition rate, different country destination, and then take the EASO data for origin destination. So after this normalization, which of course has some pitfalls, but it's a decision you have to take, then we did further cleanup. So we clean up for missing data, and we clean up for variables which have very low variance or no variance. So processes which are stable do not give you any information about what's happening next. Okay. So we try to reduce this number of like 500 variables to some reasonable number that you can work with. And this is changing root by root. So the idea that I'm conveying here is that although it would be nice to have a single migration model based on just on theory of migration, in practice, drivers of migration in a small time scale can change a lot from the theoretical willingness of the researcher to have one single model for everything. So in terms of how we detect things, of course, we apply two standard techniques. One is the change point analysis for the mean of the process. So for example, these are historical data. So this is where the statistics learn. And this is the latest period of observations. Within this, let's say, right-hand side number of data, we change for the change point in the trend. And so, for example, in this example, we see that there is an increase of trend. And then we measure also the acceleration. So what we call momentum. This is a knowledge inherited from finance. So if you want to see whether you want to invest or disinvest the money in some stock, you look at the momentum, which is the ratio between the rolling means, so short-term mean and long-term means. And if these two numbers are the same, it means that the time series is more or less behaving like the past. If it is increasing because the short-term mean is actually going up or down, then you see there is a momentum. And the momentum is where you want to put money on remove money, depending on which side you are. Then we did the same for the variance. So we took the rolling variance, and because also the change in variance is an indication of instability of the time series, which might matter the analysis. So not just the trend, but also the variance. And so we did some kind of, and so you can see here is an example of how we can spot change points in the change of the variance. And according to the fact that this variance goes to zero or actually increase, we decided to keep or not this time series in the analysis later. And then there are other things, because we don't know what the absolute value means for example, for the G-delt or even for the conflict data. We need to take into account whether, with respect to, how the last months for this data behave compared to the mean of the past data. The explanation for looking at this is, again, because, for example, as I said, there might be countries which are unstable, but they have some kind of instability which is kind of constant. It seems like a joke, but the idea is that as I said, there might be several conflicts going on, small conflict, which is kind of the normality for a country. So, and this number may be high compared to another country where there is very little conflict, but when there is a conflict, this generates lots of migration. So it's important, again, to also consider the baseline for each country differently. So the absolute value for us did not really mean something. And the same is for Google Map. We want to see whether there is some kind of deregulation in the data. And we did the same also for all the, say, official statistics. You can see all together. And we try to kind of summarize which are for this particular week and for this particular origin destination route, where are the variables which had more instability with respect to the previous periods. And in the end, what we measure, so say the dashboard of early warning looks something like this. So you have for each country of origin, destination EU in this case, it is shown. We saw how many type of signals we have. And so this is an indication of we need to keep an eye, for example, on this route for some reason. And then whether this number of signals, for example, in terms of the trend of number of applicants, is positive or negative, and whether each of these signals is a strong signal like NEL3, the red one, or it's the L1, it's a small signal. So we have a way to discriminate within the intensity of the signals. That's a dashboard which changes weekly, and it can give you information about what's going on. So after this, we went to the next step, which is about identifying correlation between variables of interest, like the number of applicants in a given country from a given country of origin, with respect to other variables. So there might be, say, asynchronous correlation going on, just because, because the processes are not going at the same time. So, for example, if I'm coming from, I don't know, from Iraq and I want to go to Germany, maybe I'm going to look at what is happening now in Turkey. So can I pass to Turkey or should I take another route? And so maybe if I do the search of something happening in Turkey, or the situation, the political situation in Turkey, is very important to decide whether in 3 months I will see people arriving in Germany, or I don't know, whatever else. And so we apply this methodology, which is called asynchronous covariance estimator. And the idea is that if you have 2 time series lagged by a theta parameter, theta is time, this just look for the maximal asynchronous correlation between 2 time series. And if it is positive, we say that then X leads Y by this amount of time, and vice versa. And so what we did, once we discovered these lags, we actually took the original time series and the lag time series in the same model. And this is what happens. So this is the correlation matrix. This is really correlation, not covariance, between all these variables in the model. And this is the correlation after shifting, let's say, each variables by the amount of time that the lead lag analysis saves. And you can see emerging correlation from this picture. So all of them are taken into account. Those that after shifting present 0 correlation are removed from the analysis. Okay, and then the model. The model is a typical elastic net model, which means it's an autoregressive model. In our case, otherwise it's just an OLS model. So this is autoregressive in the sense that we in the explanatory variables, we also put the application in the previous period, plus all the predictors in the previous period. And then we penalize this by 2 penalty functions. Okay, better than nothing. So 2 penalty functions. These penalty functions, so this is the typical OLS part, and this is the 2 penalty function, the L1 and the L2. So you take squares, the sum of the squares, or the sum of the absolute value of the coefficient that you want to minimize during the this fitting part. So there are several tuning parameters in this analysis. One is alpha, and the other one is lambda. So alpha is kind of independent of time in the sense that you decide which type of penalty do you want to use in the model. Lambda depends on the window of time we are working on. So in this case, this is an only window. Here in the example, I took 30 periods, but I think in our analysis, this is the number that you can configure depending on the speed of your time series and also the granular resolution of the time series. But anyway, we took the last 30 periods to fit the model, and we want to predict the next. So this model is such that if you take alpha equal 1, you actually remove the N2 penalty, and this is the lasso estimate, which is an OLS with the where you also do model selection, meaning that some of the coefficients are sent to 0 artificially by this optimization process. If you take alpha equals 0, you drop the L1 penalty, you have the L2 penalty, and this is the ridge regression. Ridge regression is, I mean, it was introduced to take into account autocorrelation between variables, which exists when you have hundreds of variables. You might have spurious correlation, and then the model can just crash down during the fitting because of this multiple correlation. So, and if you take alpha equal 0.5, you are in between. So you kind of take into account the model selection. So you want some of the coefficients going to 0. So you want to reduce the dimensionality of the model because you want to learn from the model. And you take into account that there might be correlations. So kind of variables which substitute one another that you want to treat automatically in the model. So that's the idea. And lambda is this coefficient, which actually is put in front of the regression coefficients, which is, I mean, if it is 0, it means that you are not applying any penalty. So this is simple OLS. If you put something positive there, it can be negative. It means that you are adding weights to the speed at which this coefficient goes to 0. So you try to force the model selection more and more. And this cannot be chosen ex ante. It requires some kind of cross-validation. And this is what we did. So we take a window of data, we run this model several times, and then we optimize with respect to MSE, mean square error, and we select the lambda, which is more or less robust with respect to all these periods. So there is a lot of, yeah. Okay. Okay, it performs quite well in terms of forecasting. And I have a table at the end, which I'm skipping, which is about how good you can do with this type of model. So this is a short-term forecasting model, meaning that the interest of the agency at the time was to predict what will happen in the next month, so 4 weeks ahead. And that's why we have this model based on weekly data, and then we have prediction at 1, 2, 3, 4 steps ahead, just to have the coverage. So it's very good. I'm skipping this. But the nice thing of this model, I think, is this part here. So this is so here you have the number of selections for this particular route, which is Syrian versus going to Greece. And these are the weekly outcome of the models. So what you see here are the number of which variables have been taken into account by the model, which variables have been selected, and also their relative weight. So if you see a red dot here, it means that this is very, I mean, highly important as a predictor for this particular week. If it is white, it means that this variable has been discarded by the model. Otherwise, you have some kind of relatively important, like medium important. So what you see here, if you observe this through time, you can see that there are patterns. So during this period of time, for example, these predictors are very important to predict this particular flow. And then during, this is December 27 to July 2018, you can see that those variables there are very important also to predict. And then in the second part of the last part of the analysis, other variables becomes more relevant than before. Like, for example, all of these variables start becoming just important predictor for the model. That's why we suggest that a single model is not really, I mean, single model means where you choose the variable and you want those coefficients not to be 0. This is why we think this is not really important. But this is hard to understand. So which variable is more important for this particular route? So we construct this plot, which is the importance frequency space, where essentially we kind of project all this heat map on this graph in this way. But here you have the relative importance from 0 to 1. 1 is the most important, 0 is we discard the variable, and this is the number of times this variable has been selected. So never and always. So you can get that for example, for route root 2 is the red root, and root 1 is another root. So predictor A can be highly important for root 1, and it is also selected many times. While the same predictor can be very, very important, although it is also selected many times. And the rest of the graph you can guess. So what gives us this graph? It gives a way to understand whether this variable is, for example, often selected but not so important, while, for example, the other one. So this is the path from Syria to Greece, and you see the most important variable, which is very often selected, is the situation of economy in Turkey, meaning that you can capture the impact of the country of transit, or the country of transit for this particular route. So it's a way to understand how it works. And then you can use this also. Sorry, it's always on top of the relevant part. So these are the same plot. Anyway, so the same plot for different zones. So you can compare for different routes from the same country of origin to different country of destination, which are the variables which have been selected most of the time by the model. So they have an impact in to predict these particular flows. Because time is almost finished, so you can do this by country of destination. You can do this by country of origin or country of destination. And for example, you can see that for people coming from Iraq, which is this color, to France, there are some variables on the top right corner which are very important. So the situation in Jordania, situation in Greece, the governance, say, index for Turkey. While, for example, I don't know, going from Syria to France, other variables are more important than those. Although it's the same people traveling to different countries. And then also at aggregate level at EU, you can also analyze these flows and see that from different countries to EU, there are different, say, push factor, which are relevant, which are kind of extracted by this methodology, and that you can later fit in a good model for this particular. I think time is over. So thank you very much.
Perfect. So good morning, everyone, and thank you for having me today. It's a pleasure to be part of this interesting workshop. So what I'm going to talk about today is measuring people displacement using Facebook data. Actually, we will see two different types of Facebook data, which I know that will be also covered by another speaker by looking at the agenda, which are the Facebook advertising platform data and Facebook social connectedness index data. Let me first start with this pretty busy figure. Last year at the GRC, together with Stefano, we published Science for Policy report where we reviewed more than 300 scientific articles or reports employing innovative data to study migration, demography, and human mobility. So the aim was to have an overview of all, let's say, the possibility out there in the literature, and we tried to categorize them by their common promises and pitfalls. I'm not going through all these data sources, which is not the scope of my presentation, but just focusing on the social media data. Let's say that they are for sure an interesting data source for researchers because they might provide useful insights where there is a lack of data in the migration landscape. For instance, they are widely available. They cover more or less all the globe. They can reach different types of populations, which are normally quite difficult to reach with traditional methods. And they also can provide timely information about different types of population. Of course, there are limitations using this data. For instance, there is a selection and geographical bias because they don't cover different populations and different areas the same way. This is basically because of the penetration rate of a specific technology, such as Facebook, for instance, which might be used a lot in Europe, but not as much in Africa, I don't know. Then there is, of course, the privacy and ethical concerns. So before using most of the innovative data, I would say, but also the social media data, we must take into account privacy concerns. They should be anonymized, not to incur into problems when trying to publish something with this data. So let's dive straight into the first of the two Facebook data that I'm going to talk about, the Facebook advertising platform. So it is not a data type, it's a platform that through an API, which is public, it does only need a Facebook account, allows a user to estimate a target audience for an advertising campaign. So it is not meant for migration research, but still researchers in the past, and also Ingmar knows it very well, have used it to study, for instance, migration stocks, estimate population, and so on. The good thing about this platform is that it allows the user to, let's say, define the target audience by different characteristics of the Facebook users, actually, which might be, for instance, their age, their gender, the education, their interests, and so on. And of course, it is available not only through different areas of the world, but also over time. So we can create actually a spatio-temporal series with this type of data. There are, of course, cons in this data. So we are not seeing actually real populations here, but we are seeing Facebook accounts, or at least, let's say, estimates of Facebook activity provided by this platform, meaning that what you get is the target audience in terms of monthly active users estimates, okay? How many users have been active on the Facebook applications and services based on the characteristics of the users that we want to know. Therefore, they are not designed to match population census estimates or their sources. So we need to take this into account and each time contextualize the use of this data for the scope that we want to deal with. There are also Facebook user reported demographics that might be not true for whatever reasons, or for instance, they also might not be updated. And last but not least, definitely, the Facebook does not disclose the nationality of their users. So we need to find a way to know the nationality somehow else. And the first case study I want to present is about the use of this data to study their potential for understanding the flows of people from Ukraine after the war has started through, towards the European Union member states. So we are talking about a country scale analysis. We started the collection of data just a bit before the start of the war in Ukraine, and we do it on a weekly basis. Still, we are doing it. We are collecting this data, meaning that each week we collect monthly active users estimates from the platform. What are the two main user characteristics that we use for this analysis? They are basically these two: the location of the users, so where the user is, and the language of the users. Why the language? Because this was the best proxy of the nationality we could find for Ukrainians nationals. Okay, so we are targeting Ukrainian nationals in this analysis, but I'm going to talk a bit more about this limitation and pros of the language filter in a while. So the limitation of the location is that we really don't know how Facebook find the users, let's say. So we basically believe that the estimates that we get are guaranteed to be correct, but we actually don't know the methodology behind. So it's kind of a semi-black box, as some data that were presented before. In the case of the location, we can also filter for different location statuses, as you can see. So we can target people that live in a specific location, or just passing by for traveling reasons, or just because they are passing through a specific location. And this is important if you want to target people that are stable in a location or are just moving. And of course, the other important filter that we are using has several assumptions, caveats, and limitations, let's say. So the first one is that Ukrainian is the most spoken language in Ukraine, but it's not the only one. The second being Russian. The problem of Russian language for targeting, let's say, Russian nationals, as you might imagine, is that many people outside of Ukraine also speaks Russian. In the case of Ukrainian language, is not very diffuse outside of Ukraine, and in particular, is not very diffuse in the European Union. So it might work better as a proxy of Ukrainian nationality. Of course, not people fleeing Ukraine are Ukrainian nationals. There are also third-party nationals fleeing the war. But according to a recent questionnaire by UNHCR, most of the refugees respondent were 99% were Ukrainian nationals. So we are probably omitting a small part of the people. And then the major problem when using this language filter is that we cannot target people under the age of 18. So this means this is a limitation of the platform. If you want to use the language as filter for the target audience, Facebook does not give you the estimates for people under the age of 18 years old. So having said all these aspects, what can we do to understand if these data are a good proxy for nationality? Well, first of all, we need to adjust a bit these estimates. We cannot use them as is. So the first thing we did was to, let's say, come up with a Facebook penetration rate, meaning that we divided the estimates before the war started, so assuming that the situation was rather stable, by the population under 18 years old with the Ukrainian citizens across the different member states. And we use this factor to adjust each of the monthly active users estimates that we get from the advertising platform. And at the end of the day, what we did was a simple correlation test to see if the two data sets, let's say, were somehow comparable. And it seems to be the case. Here we are using data from Eurostat about the number of people with the Ukrainian citizens in the various member states under the age of 18 years old, because this was also possible to do with the Eurostat data. After all this processing, we were able to get a sort of signal from this data about the displacement trajectories of these people fleeing the war. And on the left side, you can see, for instance, at the latest week we had at the time of writing the article, most people were supposedly moving towards Poland, followed by Germany. And the rest is just a list of the other member states which had an increase in these monthly active users compared to the baseline, which was the pre-war situation, above 2% level. On the right side, you can see that there is also, let's say, the whole time series for the 5 weeks that we are considering in this work. And you can also see for Hungary, Romania, Poland, and Slovakia, which are the 4 member states bordering Ukraine, that we also have a comparison, which is in the form of UNHCR data portal data, arrivals to these countries. For, I would say that except for Romania, the trend looks kind of similar. You see a bend, and it's because the thing that I'm plotting is the original monthly active estimates and the adjusted values with the method that I showed you before. This is another case study where we applied the same data to study, let's say, the consequences on this Facebook activity because of the earthquake of Turkey and Syria this February. And we are comparing now the monthly active users estimated from the Facebook platform before and after the earthquake. And as you can see, there was a huge increase. We are now looking at Turkey, and as you can see, we can go even further in detail compared to the national analysis that we did before. So we are now looking at Turkish provinces. And you can see there seems to be a clear pattern in these relative changes. The dark, let's say the red areas are where these changes are incrementing. And this happens apparently in the area hit by the earthquake and around the earthquake, which are where the star symbols are. And all the other areas saw a decrease in this monthly active usage. What we can say about this, one might argue that people is moving towards the area hit by the earthquake to provide support, but this is really just a speculation. We cannot prove this, unfortunately. What is interesting is that we can see from the data 1 year before if this happened because of seasonality, for instance, just to say, okay, this is not a signal of a shock changing the system, but it happens all the time. This does not seem the case, as you can see from the feature, comparing the same period, but 1 year before. In this case, not only we don't see the same clustering of activity, but also we can see that the relative change, the magnitude, is much lower compared to what happened after the earthquake, after the shock. There is much more activity after the earthquake than when there was none. So the second and last Facebook data that I want to talk about briefly is the social connectedness index. So this time, this index is generated by not an advertising platform, but by people working at the Data for Good team at Meta, who are also engaging researchers and university for producing this type of data. This is not the only data that they have. They also provide different data set that can also be used for studying migration, but I'm focusing on this one right now. What it is, it's an index that uses a snapshot of Facebook users and their friendship networks to measure the intensity of connection, digital connection between two locations at a specific time. So actually, we know how this is calculated because, let's say, the methodology is more transparent in Data for Good than it is for the Facebook advertising platform. You can see the equation by which the social connectedness index between location I and J is calculated. And I can tell you also that these numbers are even further processed by adding some noise to anonymize the data. They don't take into account, for instance, Facebook users when they are too few people because of privacy concerns. And we try to use this type of data to always in the context of the war in Ukraine. On the left, you can see the social connection between the various regions in the European Union and Ukraine as a whole, as a country. And the darker, the more connected these areas are with Ukraine. I'm speaking of connection when I'm talking about connection. I'm talking about friendship networks, meaning the digital friendships of Facebook. And we try to use this data to estimate the diaspora at regional scale. Actually, it was not the only variable entering the system, but there are also a few other readily available variables, just like the total population in the destination country and the location of the various areas. But as you can see, for these specific 5 member states, this social index seems to work pretty well in estimating the diaspora. Why we are doing this? for this main reason, because diaspora is one of the major drivers of migration, and because at this spatial level, it's not that common to have this type of data at least updated all the time or released in a timely fashion, I would say. So this should fill a gap in the migration data landscape that we don't have. So our future research, of course, will further investigate on the use of this indicator to study, to predict also the migratory flows. So we can use diaspora, of course, because the literature is telling us that it's the major driver, but we can also try to use this same indicator as a part of our modeling. And not only for Ukraine, we want to know if this is also valuable for other countries as well. This is just another example of a study that employed this social indicator to study migration. It's a work made by Rao et al., and they identified potential settlement areas in host countries based on the social connectedness measured by Facebook and the high level, the increase of population in the various areas. So in red, you find what the authors think are the potential settlement areas for Ukrainian refugees. And this would help anticipate, for instance, the migratory flows or help managing the migratory flows. The very last slide, what are the main takeaways of this presentation on Facebook data? The good thing about this data is that they provide timely information and they are very diffuse, although they don't cover different areas and population at the same time. So we always need to be aware of this limitation. We need to validate them, if possible, with official statistics. It's not always possible, as we were saying before, using innovative data. But at least if you know they work somewhere, we might think we can apply them to other cases as well. But still, we have to take into consideration the context. In the case of Turkey, for instance, the government shut down the social media, Facebook, for instance, usage for a few days. It was not the case of the figure I showed you before, but the following weeks, the signal was not that present as we hoped, for this reason, probably. The methodology is not always transparent, although as we saw for the data made by Data for Good team, it's a bit more transparent than it is for the Facebook advertising platform. And I would say that in the end, these type of data are best when combined with official and traditional data. Just like we saw with Google Trends, is very useful when combined with other type of data, even if they are not official but operational, but still they are recognized as meaningful data in the field of migration. Thank you.
I was setting up, as far as I know, Facebook also let go of quite a few people in the Data for Good team just a couple of days ago, right? Like sort of, so there also those things are always moving. And some of the data sets that used to be open are no longer open, sort of. So there's also some, yeah, one has to see how things are developing there, unfortunately.
There.
Great, yeah, good. Thank you so much. Excellent. Yeah, thanks for the invitation. Okay, 15 minutes, 38 slides. Let's go. Okay, so let's see. Okay, so what I just joined work with a number of people, so including at my previous institute, so the Qatar Computing Research Institute, in particular Marie Rufner, who's done some analysis you'll see later. And then at my new institute, I'm building up a team there. And so this is still sort of, you know, they will sort of contribute, but then they contributed much yet. Basic question is, what kind of population changes can we see from space, right? So at the very high level, of course, all of you have seen sort of these sort of time-lapse videos, right, from Google Earth, where you sort of see whole cities expanding or sort of, right? And of course, but this is on timescales we might not interested in this particular workshop, right? Obviously, there's still a signal there, right? Other sort of things that might be of relevant that we are not working on in our team, right? Sort of like refugee camps and how they are sort of growing, or sort of, so again, their sort of work on that using satellite imagery in particular, right? Sort of so automatically detecting and counting tents and sort of relating that to refugee flows. Somewhat related, there's work on detecting damaged buildings, right? You would imagine that if a building is damaged in an earthquake, right, then people no longer live there. They have to go somewhere else again. So it's also somewhat relevant, but it's not work that we're doing in our team. But again, there is a lot of work out there that does this type of work. So what we are interested in is whether we can detect refugee movement in satellite images. And we started this thinking about this a couple of years ago, mostly in the sort of Syrian context, right? We were wondering, sort of, can we see something, you know, related to this phenomena from space? There could be two basic approaches on how to do this. So on the left is you try to sort of capture flows, right? Like in the moment, right? If there was like enough satellite images, right, you would sort of, you know, hope that you can capture like queues on roads, right? And you sort of count, oh, there are a lot of cars going in this direction or sort of so, right? Like sort of so, right? And the other approach sort of so is more like about sort of stocks, where you have sort of before and after images, and you sort of see that cars have disappeared, right? So far, we are mostly focusing on the second one, although but back to the first one, mostly related to sort of data availability, right? Sort of to be able to do this, what you need very, very highly updated sort of imagery. And so initially, so we went with the second approach, right? In terms of actually sort of detecting cars, so there's existing work out there, so you don't have to reinvent sort of object detection and computer vision. What we are using for, at the moment, just sort of for this sort of preliminary analysis is work that was done in this paper related to sort of analyzing COVID-19, you know, related sort of things. And the people were kind enough to put their sort of, you know, model and everything sort of on GitHub. So this was, of course, very helpful. In their work, they were interested in COVID-related sort of changes to mobility, right? We can sort of see this is a parking lot of a car rental location, and then sort of, you know, after COVID, right, none of the cars were rented out, right? And similarly above, you see sort of airports where a lot of planes are sort of grounded. On the right, you see the performance of their sort of object detection for a number of different sort of classes, sort of small objects, medium objects, darkish blue, black is sort of large objects. And for this work, we are using this sort of small car class, which has like an okay performance. It's around sort of 0.5 mean average precision map, but so I mean, you'd see some other variation later. So it sort of kind of works okay-ish, let's say, sort of, or so, not perfect. So with that detector already existing, so question is, okay, how do we get data? So in my previous institute, we actually paid for accessing Maxar's platform. So Maxar, or, you know, sort of owns Digital Globe, is sort of the main provider of digital or high resolution satellite images. So on most sort of, you know, Google Earth or Google Maps images, if you zoom in, you know, at the bottom, it would say sort of copyright from Maxar or Digital Globe. So with that access to this platform, we selected a couple of locations. So we started in, for example, in Syria, looking at Al-Bab, and then you could sort of see the temporal availability, right? Which sort of varies, right? Like quite a bit, right? Sometimes we have like sort of several pictures, you know, within a month, and then there's sort of like other periods where you go several months without any pictures. So it's not a fixed update frequency, right? Basically depends on sort of market demand, right? Like if there's something actively going on, right? So then they might sort of point the satellite and sort of take a snapshot. If there's nothing going on, you know, there can be sort of months without updates. And then, you know, we did some additional filtering, cloud coverage, which in the case of Syria is not much of a problem, but, you know, Ukraine is a very different sort of beast. So we said not more than 10%. We filtered on maximum ground sampling distance, GSD, so resolution 50 centimeter per pixel or higher. And so then, you know, we got the imagery, we ran this existing model, right, sort of detected a bunch of sort of cars, in this case for Al-Bab. How well does it work? So here on the left, we have manual annotation. On the right, you have sort of the computer output, right? Sort of, so it looks okay, sort of, so, right? I mean, and sometimes even the manual annotation, it might not, and it's sort of hard to say, right? To see there in this part, there's sort of something where the manual annotator thinks it's probably not a car, right? There's sort of something detected there where you can sort of see a clear difference between the two. Overall, though, again, it works sort of fairly well, or at least in this sort of best case scenario, right? Like it's completely cloud free. This is 30 centimeter imagery. It's the best possible available imagery, sort of, so you get like an accuracy of sort of close to 80%, which at least for this particular type of model is probably an upper bound. Of course, you know, the models are continuously improving, but I mean, there's sort of like an upper bound. At some point, you know, you start hallucinating sort of things, right? Because it's really not clear if is this like a picture, is this a car or not. So then, with this sort of car count, so what do you actually observe? Do you get something that makes sense? Here's just a preliminary validation in the Syrian context. So on the left, you have car counts for the city of Al-Bab, where there was actually active fighting. And so the fighting happened during this period, marked in green. I don't know why, but anyway, sort of so, and you can see as the fighting approaches, the number of cars detected goes down quite a bit, sort of so. And even before, there is definitely fluctuation, but not quite at this sort of level. So this is also in terms of sort of time scales, quite rapidly, right? So this is October 19th to sort of December 8th, right? In that period, sort of like 90% of the cars essentially disappear. And after the fighting, they seem to sort of return. So for reference, this is another location in Syria where there was no fighting. There's also some fluctuation, sort of so, and we sort of see later different factors that might contribute to sort of this sort of normal fluctuation. Of course, this is sort of Syria now. What's more interesting is sort of Ukraine. So here you have sort of two pictures of Kherson before and after the invasion, where you can sort of just visually sort of see there are certainly fewer cars being detected, right? But then these pictures are also different in many ways, sort of also, right? Like sort of so there's the lighting is somehow different, right? Shadow length, the nadir angle, whether the satellite is right overhead or not, is different. There might be different times of day or week, right? Maybe people are just now at home or in the office or parking underground, sort of so, right? So just from sort of two pictures alone, it's sort of hard to say, but again, at least it gives something plausible. And in this case, in Kherson, the number of cars sort of going down. So let's drill a bit deeper, sort of in terms of what the issues are. So, for example, one of the things that always comes up in these models is sort of some sort of precision recall trade-off that you can kind of basically tune. So what you can hear on the left, this is somewhere in Ukraine, I've forgotten where exactly, where for the same, I mean, the model comes with sort of different confidence thresholds. Like for everything detected, the model tells you like something like resembling like a probability, right? Like it's like 10% confident or 20% or 50 or 90% confident that it's a car. And now we sort of see different sort of thresholding applied, right? Sort of so in red basically is a sort of like a sort of superset, sort of red and yellow basically together means red. So anything at least 15% confident would be considered a car, and then in yellow at least sort of 45% confident is a car, right? And you can see here that the red, for example, picks up quite a few things that clearly are not cars, right? So this is actually on the roof of the building. This is sort of like air conditioning units or something like sort of ventilation units or sort of okay. So and this actually we just also saw in other parts of cities in general, where sort of things on roofs look like they could plausibly be cars, right? If you sort of see this in isolation, right, it's like a road around, right? So this could be a car, right? But it's not, right? So now how do you sort of, but then maybe this is actually a car, right? So now if you go for the yellow threshold, like you would miss this, right? So how do you sort of tune your precision recall? Right? And so in particular, what's more important? So for our work, we decided that precision is more important, that what we want to detect is really should be cars. We are fine with leaving out some cars as long as the things that we detect are cars, because we only want to detect things that are mobile, that could go somewhere else, right? So it's not just about sort of mapping all the cars in the city, but we only want to detect something, some sort of markers that people could take with them and take somewhere else, right? And so we use this sort of, if you're familiar with sort of data science, sort of S0.5 score. It's a variant of sort of F score that gives more weight to precision. And then we looked at sort of, so this, we annotated some data still in the Syrian context. We looked at one, if we change the confidence threshold, how does this sort of this objective function sort of change? And then there's sort of some optimal sort of point, which in this case is around this sort of 0.45 value, right? So going forward in all the results, what you see is this cutoff of 0.45 for confidence. Great. So now we sort of some kind of validation for sort of detecting cars with reasonable precision, sort of. So, but of course we're not interested in cars. We're interested in people, right? Sort of. So how do we now link people and cars? So this is, I think, averaged across a couple of months, sort of pre-war cars in Kiev. So seeing in sort of these grid cells, you see the number of cars detected, right? And we also have sort of pre-war people, right? And sort of you see they're somehow related, but it's not as straightforward as we sort of thought, right? So you get a sort of kind of relation like this, right? So if you sort of compare the individual grid cells, right? So for example, here you have quite a few people, but very little cars, right? Maybe these are high-rise buildings and there's no outdoor parking, something like this, right? So overall, you get a relationship like this, right? So you can fit this in various ways. So my colleague used the sort of GAM model, generalized additive model, sort of to fit this. And now once you have this sort of relationship between cars and population, you can then sort of go and sort of apply it going forward to link the for this specific city, to see how the population, how the sort of car density sort of changes, and what would that mean for actual people, right? So now these are not estimates of cars, these are estimates of sort of people, where you have sort of like a pre-war baseline for Kiev, and then based on the number of cars, you have sort of estimates for the number of people. Now, these are averaged across several images in a month, right, or so. And so this is already one caveat in terms of temporal resolution. Now, how plausible are they? So this is now a report from early March, where supposedly half of the population here had left, right? So here, actually, this would indicate an even bigger drop. It's also not quite, depends on when these pictures were taken in March, right? So definitely a drop that's plausible. Whether half or not, yeah, hard to say, but at least just give some sort of plausibility that the directionality is plausible. This is a city on the west of Ukraine, where you see the number of cars going up. So this is on the border with Slovakia, and at least this sort of its upwards trend is again sort of plausible. Here, there's the reported estimates that the number of people have now at least tripled. And this was a report published also now in March. So then it depends on when these pictures were taken that go into this, but at least the directionality is sort of plausible, right? And there's some other sort of hand-waving plausibility results. This is now sort of for all of Ukraine. I think that this was in April, April or May. I have to look at but compare sort of pre-war with post-war sort of changes, right? And you sort of see large point of Ukraine sort of going sort of down, right? So cars, and therefore most likely also people disappearing, and actually the West seeing an increase in the population. So punchline for this part. Oh, okay, audio. Okay, I have to hurry up. It sort of works, but the main difference, the main difficulty is data sparsity, right? So here you have sort of cities, and every row is the month, and you see like all these black areas. There is no, right? So for this city, right, we go several months, like until you have like a picture, and then again several months until you have a picture, right? So for something like more recent sort of, so it's difficult sort of to do something, right? And so we ask ourselves, can we do something using planet imagery instead? So planet.com imagery. So planet.com is another satellite imagery provider where the main trending point is daily, right? So daily Earth observation data, right? So what do these pictures look like? So here on the left, you have a picture from Brussels, right? And you can kind of see there's something on the road, right? These are probably trucks, right? And there's something probably here sort of or so, but you certainly can no longer see individual cars. Big trucks maybe, but certainly not individual cars. Right? And similarly here, this is a picture on the Ukrainian-Polish border, where you can, there's probably something there, probably a queue of cars, but sort of counting cars or detecting individual cars is difficult. Data availability is much better though. So here, for most days in Brussels, you have a picture. Where you don't have a picture is due to 100% cloud coverage, right? So for example, for Death Valley, you have a picture every day, right? There are very, very few clouds there, right? So now if we want to use such images, but without actually seeing individual cars, how do we get training data, right? Like how would we train a model if we cannot actually annotate individual cars, right? So one approach is you use a high resolution image, right? Sort of right? And you annotate the cars and you sort of count, okay, this picture has 4 cars, and then you transform it to like a low resolution image, right? Still higher resolution than actual planet imagery, but something sort of like this. And now you sort of showing not a detection, but a regression problem, right? We say, okay, here the answer is 4 cars, right? I don't know where they are because they might no longer be individual seeable, but there's some change in terms of sort of ground reference or something or sort of so. So please just tell me that there are sort of 4 cars. This might work, but then there are a lot of things how this is not exactly what planet imagery does. For example, this might come from different times of day. This might relate to different shadow lengths, etc., sort of. So punchline in the end, we still want something that is sort of proper, sort of ground truth, right? So we want to take something that's temporally aligned. How could we do this? One data source is traffic from Google Maps, right? Where we can sort of see when the image was taken on the planet. This was the sort of traffic pattern in Brussels, right? And we can sort of overlay and basically use this as sort of a kind of like a weak annotation for the computer vision model, right? So and there are some drawbacks with this, but I think this will sort of work. Another data source is also from Google Maps, where you have this live in-store traffic, right? Where you can sort of see, okay, at this time when the picture was taken on planet, so this store was so and so busy, right? Like so this would be of use for parking lots. So would be another sort of weak annotation. And then the last thing we want to do is actually look at webcams, right? So for webcams, again, you know exactly when this picture was taken. This is somewhere in Brussels. And okay, when the satellite took a picture, there were like 3 cars there and 5 cars there. And then you can sort of, again, validate your model. Okay, so sorry for the sprint. Hopefully it was somewhat interesting. So to recap, again, we looked at this, considering these sort of 2 different types of satellite imagery, the high resolution satellite imagery, right? Sort of so where detecting individual cars is mostly feasible, sort of so, and you get something that's sort of high level plausible, but biggest challenge is the temporal sparsity, right? Again, sort of so if you have a picture, you can do something, but if you don't have a picture, there's not much you can do. Also, the car detection, if it's especially if you go to the 50 centimeter ground sampling distance, is far from perfect. There are a lot of different sort of things that still get in the way. If you look at sort of low resolution from planet, sort of like 3 meter ground sampling distance, that's great. You mostly have daily imagery, except for cloud coverage. Again, cloud coverage is still an issue in Ukraine. Also, access is much more affordable, right? This is quite generous, sort of free access for academics. But now we still have to figure out the computer vision part, right? Because we can no longer detect. It's no longer about detecting objects. It's about sort of counting without detecting. And this is something we're working on. And then I'll add with a bit of one advertisement. So later this year, we'll have a kickoff for a new institute that I'm founding, which is the Interdisciplinary Institute for Societal Computing at my university. So if you're interested in this, talk to me during the coffee break. We'd love to have some of you attend. So in a nutshell, there's sort of 2 strands that we're working on. There's computing of society, which is all about measuring, sort of things like migration and gender gaps and other things. But then also computing for society, which is about sort of working with stakeholders on these topics. So hopefully improve things ever so slightly. Yeah, thank you very much.